Now we study quadriphase shift keying. So in quadriphase shift keying or QPSK, we are transmitting four phases for die bits, that is two binary bits are grouped together. Therefore, we have four signals. I is equal to 1, 2, 3, 4 for t duration we are transmitting. So the general equation which represent the signal is as shown here. You go on substituting the values for I here. You are going to get four different phases: 45 degree, 135 degree, 225 degree and 315 degree. So in QPSK we are using four phases, that is why the name given quadriphase or quadraphase shift keying. Signal space diagram for this QPSK is represented by this equation. So let us expand this equation using simple trigonometric relation. Cos of A plus B is cos A cos B minus sin A sin B. So you go on substituting the value for I here from 1, 2, 3, 4. Here also from 1 to 4. So when I is equal to 1, cos of pi by 4 is 1 by root 2. Similarly here sin of pi by 4 is 1 by root 2. When I is equal to 2, 4 minus 1 is 3 pi by 4, cos 3 pi by 4. Here also sin 3 pi by 4. So if we consider orthonormal functions, here we are able to find cosine signal and here we are able to find sine signal. So these two signals represent orthonormal basis function, that is the carrier with amplitude phi 1 and phi 2. If we consider gray encoded bit, which is 2 bits, that is called die bit. So for each die bit combination, phases are as shown. So for 1 1, 45 degree, that is pi by 4. For 0 1, it is 3 pi by 4. For 0 0, it is 5 pi by 4. And for 1 0, it is 7 pi by 4. So how to find the coordinates in order to write the signal space diagram? So in order to point the phase, we need the coordinates here. Therefore here, so let us try to put the value of I as 1 here. So when I substitute the value of I1 here, so I am going to get here root e by 2 and here also root e by 2, because both are positive. Sine and cos are positive in first quadrant here. So 3 pi by 4 means here we are going to consider here the trigonometric relation ASTC. All are positive, sine are positive, tan are positive and cosine is positive. So here we have cos term 135 which is negative and I have sine term which is positive. If we consider 5 pi by 4 for I is equal to 3, which falls in third quadrant, according to trigonometric rule ASTC, tan are positive, therefore cos is negative and sine is negative here. So in fourth quadrant, cos is positive and sine is negative. So now we have obtained the coordinates of the message point, that is 4 message points. So now let us try to write the signal space diagram. So we have the coordinates square root of e by 2 plus and square root of e by 2, that is x and y coordinates. So locate here. So on x-axis we consider the orthonormal function first and second orthonormal function on y. So this is the location of the message point 1 1. Similarly, locate the other points here for 0 1. For 0 1 it is second quadrant, for 0 0 it is third quadrant, and for 1 0 it is fourth quadrant. So this represent the signal space diagram for the QPSK signal. So the next very important concept is how to generate QPSK signal. So here we are getting the binary data sequence. Before it is converted to a QPSK signal, we have to convert this binary signal into some encoding format. That encoding format we use here is polar non-return to 0, because we have here in our table only two values, these two values plus or minus e by 2. Therefore, divide that bit sequence into even and odd number and multiply that with the orthonormal function or the carrier function cosine and sine, and then add the phases of this in order to get QPSK signal. So in coherent detection of QPSK, the received signal x of t, which is multiplied with the known carrier function, this is cos and this is sine. So there is one inverter here in order, that is a phase shift here in order to get the sine signal from the cosine. Now we are applying the signal to the integrator in order to generate the value x1 and x2. So this value is compared with the zero threshold value of the decision device. So here there is a multiplexer. So if the threshold value, whatever decision device, if x1 is greater than 0, decision device will generate 1 here and decision device will generate 1 here if x2 is greater than 0. So this 1 1 is available at the output of multiplexer. Similarly, for other combinations 0 0, 0 1, 1 0 and 1 1. So that is how the QPSK signal is detected, binary signal is detected from. Now we'll try to understand error probability of quadrature phase shift keying, that is QPSK. So the received signal at the input of receiver is given by x of t is sum of transmitted signal and the noise of the channel. So we are transmitting finite time duration signal in QPSK. There are four phases: 45 degree, 135 degree, 225 degree and 315 degree. So here, if x of t is available at the receiver input, from the block diagram of coherent detection, we want to obtain the value x1 and x2. That is the integer value I have to obtain from the correlators here, which is shown in phase channel and quadrature channel. The expression for the value for the random number, that is x1, that is given by multiplying the received signal with the orthonormal basis function or the carrier function. So whatever we have used at the transmitter. So substituting x of t equivalent and using the orthonormal property here. So we are going to get the expression square root of e cos 2i minus 1 pi by 4 plus w1. So here Substitute the value for I from 1, 2, 3 to 4. You are going to get the expression for this term, that is plus or minus square root of e by 2. For example, if I is equal to 1, cos pi by 4 is 1 by root 2. Therefore, I am going to get here plus root 3 by 2 plus w1. If I is equal to 3 pi by 4, that is 135. Cos is negative, therefore I am going to get minus root 3 by 2. In a similar way, the vector value for the second signal, that is quadrature channel, is given by x2, which is also oscillating between two values plus or minus square root of e by 2. Since in QPSK, we notice that 2 bits are transmitted per symbol. So the transmitted signal energy per symbol is twice the signal energy per bit. Therefore, these are the observable vector, which are sample values of independent Gaussian random variable with mean values, that is equal to plus or minus square root of e by 2 to minus or plus square root of e by 2, with a common variance, that is n naught by 2. Therefore, we can express average probability of bit error in phase channel and quadrature channel of coherent detection of QPSK signal that we have shown here by this expression. So what is the average probability of correct detection, because we have two channels working together here? That is given by probability of correct detection is given by 1 minus p dash whole square. So substitute what is p dash here and expand using a minus b whole square. Therefore, here we are going to consider the average probability of symbol error of QPSK is given by probability of symbol error, that is equal to 1 minus average probability of correct detection. So when you substitute this PC expression here, we are going to get the final expression like this. So here always E by n naught, that is energy by noise, is much greater than 1. Therefore, we can ignore here the second term, that is this one. Hence, the average probability of symbol error for QPSK receiver is approximately equal to twice the Q function here. So we are able to see here the signal space diagram that is shown for QPSK with the orthonormal basis function, that is n is equal to 2, phi 1 and phi 2, and for m is equal to 4, there are 4 message points observed here: 1 0, 0 0, 0 1 and 1 1. The next very important concept here is to draw QPSK waveform. Here we have considered gray encoded input bit, and we have assigned the phase of QPSK in radians for these gray encoded input bit. If the input bit is 1, binary 1, for TB duration, we are going to transmit in phase of the signal, and for 0 we are going to transmit out of phase of the signal. And we have to remember here, as there are two channels, that is in phase and quadrature phase channel, here we are multiplying with cosine and here we are multiplying with sine signal. Therefore, let us consider the input binary sequence 0 1 1 0 1 0 0 0. Since QPSK is using die-bit configuration, so let us group the binary stream into die-bit, that is first die-bit, second die-bit, third die-bit and fourth die-bit. So out of these die bits, you separate odd bit and even bit. So always the first one is odd bit, second one is even bit. Always for odd bit here, we are going to use the cosine in phase and out of phase signal. Since the first odd bit is 0, I am transmitting out of phase cosine signal for TB duration. So the next odd bit is 1 here. I am transmitting immediately after this TB duration in phase cosine for TB duration. Since the next odd bit is also 1, the carrier continues with its phase and it ends here for TB duration. The next odd bit is 0, therefore out of phase cosine signal we are transmitting. In a similar way, from the binary sequence, extract the even bit binary bits, that is 2, 4, 6, 8. Observe the polarity, whether it is 1 or 0. If this is 1, transmit in phase sine signal for TB duration. If the bit is 0, transmit out of phase sine signal. Since again here bit is 0, out of phase signal is continued here up to this duration. Now, in order to obtain QPSK waveform, we have to add phases of these two, that is S1 of t and this one Si1 phi1t and Si2 phi2t. The phases at each point is added and we can write the final QPSK waveform. For example, here the phase is negative. At this point phase is 0. Therefore, 0 plus negative is negative here. So let us consider the 0 crossing here. Here phase is 0. Here phase is maximum. Therefore, we have the maximum phase, that is positive. At this 0 crossing, we are able to see 0 phase. Here we are going to see minus, that is negative. Therefore, 0 plus negative is negative here, negative phase. And we'll check what is the phase at this 0 crossing. Here the phase is negative, here the phase is 0. Therefore, 0 plus negative is negative. So like that, we can write the phases at the crossing. That indicates that the quadrature phase shift waveforms here. So the next very important concept here is M array PSK. Here in QPSK, we used to transmit 4 phases, that is pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. Where in M array PSK, the phase of carrier takes one of m possible value. In BPSK, we transmitted two phase 0 and 180 degree or 0 or pi radian. In QPSK, the value of m is 4. That is 4 phases we transmitted. Now, in M array PSK, we are going to transmit m possible values of the phases, one of the m possible values. So, accordingly, that equation is represented like this. Si of t, signal is to be transmitted, is given by square root of 2e by t cos the frequency, that is carrier frequency, plus 2 pi by m into I minus 1. Here you go on substituting the value for I from 1 to m. For example, here we have consider the value of m, that is number of possible values of phases to be transmitted is 8. Therefore, on substituting m is equal to 8 here, 2 pi by 8 is nothing but pi by 4. Therefore, substitute I from 1 to 8 and you will get the phases like this. First one is for I is equal to 1. Here I, that is 1, 1 minus 1 is 0. So pi by 4 into 0 is 0. Here is the first message point. For I is equal to 2, 2 minus 1 is 1. So 1 into pi by 4 is pi by 4. Similarly, for I is equal to 3, 3 minus 1 is 2. So I am going to get pi by 4 into 2 is pi by 2. So in one quadrant, I am going to get the three phases 1, 2, 3. So I am going to get 8 phases here 1, 2, 3, 4, 5, 6, 7 and 8 phases. So the bit rate for this MRA PSK is given by RB is equal to reciprocal of bit duration. So here we can observe there are 8 message points. So how to identify the decision boundary? So the decision boundaries for this is as shown here. So the decision boundary for the different message points identification, first message point, second message point, third message point, fourth, fifth, sixth, seventh and eighth message points. Channel bandwidth for this QPSK MRA QPSK is given by bandwidth is given by 2 RB by log 2M. So what will be the bandwidth efficiency of M array PSK? That is given by rho, that is given by RB by B. Substitute the expression for B here. We are going to get the final expression after simplification log 2M by 2. Now we will try to identify what is the effect of increasing the value of M with respect to bandwidth efficiency. So for BPSK, M value is 2. So if we substitute 2 here, log 2 base 2 is 1, therefore 1 by 2 is 0.5. For QPSK, M value is 4, therefore log 4 base 2 is nothing but it is 2, 2 divided by 2 is 1. If I substitute M is equal to 8, log 8 base 2 is nothing but here I can write log 2, 2 to the power of 3. Therefore, log 2, 2 to the power of 3 is nothing but 3. 3 by 2 is nothing but 1.5. Similarly, here we are going to get for 16, 32, 64 the increasing bandwidth efficiency. It states that as the phases increases, number of phases transmitted increases, the bandwidth efficiency also increases. The next configuration is M array QAM, that is nothing but here in M array PSK we interrelated the envelope which is constrained to remain constant, that is nothing but in phase and quadrature components are constrained to remain constant here. Therefore, because of this, the constraint manifest the result in a circular constellation for message point as shown here. So if we want to free this in phase and quadrature component, then the new modulation scheme we obtained, that is M array QAM, M array quadrature amplitude modulation, where this is a hybrid type of modulation. Here the carrier experiences amplitude as well as the phase modulation. So the basic single space diagram for one dimensional PAM. This is the basic digital modulation, M array phase amplitude modulation. So here M array pulse amplitude modulation, one direction, one dimensional. Therefore, for this we can generalize two-dimensional QAM from M array PAM, that is the basic modulation. So that is given by this one. So the two orthogonal constellation of 4 array PAM for M is equal to 2 here, M is equal to 4 here, there are 4 states, message point. If we consider two orthonormal functions phi 1 and phi 2, we can see the horizontal constellation and vertical constellation here. So write the message point 11100001, and the distance between these message point is D here. So from this we can write M array quam for M is equal to 4, vertical constellation and horizontal constellation. From this M array quam for M is equal to 4, we can obtain signal space diagram for M array quam for M is equal to 16. How to obtain? Let us see. So there are 4 quadrants here, 1, 2, 3, 4. So we are going to write in first quadrant the components that is present here. So here the rule is you have to write the vertical constellation from top to bottom and the horizontal components from left to right. So what is the vertical component? That is 1 1 and 1 0. What is the horizontal component? 1 0 and 1 1. So write it and concatenate it. 1 1 1 0, 1 1 1 1. Similarly 1 0 1 0, 1 0 1 1. So this is the first quadrant constellation. Follow the same for second quadrant constellation. Write the second constellation element top to bottom, again left to right, again left to right, and write this pattern. For third quadrant, write top to bottom, that is 0 0 and 0 1, and left to right is 0 1 to 0 0. Similarly for fourth, 0 0 0 1, and here 1 0 1 1, and concatenate the bits, you will get 16 different states here. So when you are going to get 16 different states here. That is how we can obtain signal space diagram for M array quam for M is equal to 16.